In this unit, we're going to be spending some time talking about acid-base chemistry, but before we get to acids and bases, we have to understand the basics about solutions and how they form in typically water as our solvent. So when we talk about solutes, solvents, and solutions, a solution itself is just a homogeneous mixture. And we said earlier this year that a homogeneous mixture is a mixture in which there are no distinct layers when the two substances are mixed together. Now, the two components of any solution are the solvent and the solute. Typically, the solvent is the substance that's present in the highest quantity. It's also the substance that is doing the dissolving. Most times in chemistry, water is going to be our solvent. When we talk about the solute is the substance that's actually being dissolved by the solvent. Typically in a homogeneous mixture or in a solution, the solute will be present in a lesser quantity, and that's an easier way to keep the two things straight. When the solvent and the solute mix together, a solution is formed, and we end up with a homogeneous mixture with no distinct layers. When something dissolves, it doesn't just happen instantaneously. It takes a few steps for it to happen. When you pour salt into water, it looks like it disappears, but it's not really going away. It's just breaking up into such small pieces that we can no longer see the salt particles. When salt hits the water, NaCl, sodium chloride, is a ionic crystalline solid. It's locked together with those positive and negatively charged ions that are bonded together. But as soon as it comes into contact with the solvent, which is water, water molecules themselves are polar. They have a negative side and a positive side. The positive side of water comes into contact with the negatively charged ions because opposites attract, and the same is held true for the negative side of the water molecules and the sodium ions. They also attract. And because of that, the water begins to slowly rip apart this crystal lattice until it's no longer stuck together as a crystal lattice, and the ions are free to float within the water. Now, when we measure how much of a solute is dissolved in a solvent, we measure it in terms of concentration. Concentration is simply a way for us to put a number to the amount of solute that is dissolved in the solvent. When we measure concentration, it can be measured in a few different ways. One of the ways that it can be measured is how many grams of the solute are dissolved per 1 liter of solution. And when something becomes more concentrated solutions simply just have more particles of the solute dissolved. So if something is more concentrated, it simply just has more of whatever that solute is in the solvent. One of the ways that we measure concentration in chemistry is with a specific unit called molarity. It has the word mole in it, so we do measure the number of moles of solute dissolved per liter of the entire solution. The units of molarity are given to us as moles per liter, or sometimes that's abbreviated as a capital M, which represents molar. So now let's take a look at these three different solutions down here, and you can see that this solution has a 0.5 molar concentration. And what that means is there's 0.5 moles of sodium chloride dissolved per 1 liter of the solution. If we have a solution that is 3 times more concentrated at 1.5 molar, it's going to have 3 times as many tiny little sodium chloride ions floating around than the solution that is less concentrated. When we calculate molarity, it actually has some symbols that we use, the same symbols that we used for moles. For the ideal gas law, we use lowercase n. We use V for volume. So the molarity, or the concentration of a solution, is given by the number of moles of the solute only divided by the number of liters of the entire solution combined. We can represent our final label for molarity as either moles per liter, or we can simply just represent it as capital M. To calculate molarity, we set up our problem in a very similar way that we've set up other types of math equations in previous units. When we're trying to find the molarity of a solution, I identify my givens. I'm given the fact that I'm dissolving 0.150 moles of NaCl, and that's going to be my lowercase n. I know that I'm making 2 liters of solution, so that's going to be my volume, and after I declare my variables, I need to know what equation I'm using to solve for the molarity. Molarity is given by number of moles divided by number of liters of solution. I simply substitute those values in, and then I can divide the number of moles by the number of liters to find that my final concentration is 0.0750 molar. When we represent concentration, sometimes we put the substance inside of brackets, and that's a symbol that we use in chemistry to represent the concentration of sodium chloride. So the final concentration of this sodium chloride would be 0.0750 moles per liter, or molar. Now, if we're provided grams instead of moles, it simply just adds one more step to the solution of the problem. Now, the other thing to watch out for is that when we define molarity, we define it in terms of liters of solution. So if we're provided milliliters of solution, we have a little bit of unit conversion to do before we actually solve the problem. Before I can find the number of moles of lead-2 nitrate that are in this solution, I need to find, well, what is the molar mass of lead-2 nitrate? So using my periodic table, I can look up the molar mass of lead, add that to twice the molar mass of nitrogen, and 6 times the molar mass of oxygen. I combine all of those masses together, and I can find that the molar mass of lead-2 nitrate is approximately 331.20 grams. I do my simple unit conversion. The grams are going to cancel out, and I'm left with 0.0302 moles of lead-2 nitrate. The other thing that I need to do with my volume is I know that I need to be in liters. There are 1,000 milliliters in a larger liter. So if I do my simple one-step unit conversion and divide by 1,000, I can determine that my entire solution has a volume of 0.200 liters. The final step is to simply take the number of moles and divide it by the number of liters, and that will give me a molarity of approximately 0.151 molar. These are 2 problems that I would like you to work out. Pause the video, give yourself enough time to work these 2 problems out, and we'll go over the solutions momentarily. For problem number 1, I am given that I have 50 liters or 50 milliliters of solution that I would like to make by dissolving a certain mass of potassium iodide. So the first thing that I need to do is I need to use the mass of potassium iodide to simply just convert the grams into moles to find the number of moles of Ki. Once I find my number of moles of Ki, I need to make sure that I've converted my milliliters to liters by dividing by 1,000. To solve for my molarity, take the number of moles, divide it by the number of liters, and that will give me the concentration of potassium iodide in that solution. For number 2, we have a little bit of a different setup. We have the number of grams of KOH, or potassium hydroxide, that are going into this solution, but now we're solving for volume, so we just need to do a little bit of rearrangement with our molarity equation. The first step that I follow is I take my number of grams of KOH, and I simply use the molar mass of KOH to get it converted into moles. The number of moles are 0.00891 moles. And what I did was I simply took my molarity equation. Molarity is number of moles divided by volume, and I simply rearrange this equation to isolate for my unknown, which is capital V. Volume is equal to the number of moles divided by molarity, and watch what happens to the labels when we substitute our numbers in. The number of moles go in my numerator, the number of moles per liter go in my denominator. Moles are going to divide out with moles. I'm left with dividing by 1 over liters, which then turns into liters in my final answer. Now, this question is asking how many milliliters of solution will be needed, so I would simply just multiply this number by 1,000 to get it converted into milliliters, which would be 89.1 milliliters. For a quick concept check, let's take a look here at this situation where we have a certain concentration of aluminum nitrate, and we want to look at the concentration of various ions in that specific situation. Now, if the concentration of aluminum nitrate is 0.150 molar, that means that for every 1 formula unit of this compound, I'm going to get 1 aluminum 3+ ion, but I'm going to get 3 nitrate ions when this ionic compound dissolves. So to figure out the new concentrations of the ions that will form, I simply can say that 1 of these ions will form for every 1 of these that dissolve, so the concentration of aluminum should be the same, but since I know that I'm going to form 3 nitrate ions for every 1 of these compounds that dissolves, the concentration of nitrate would simply just be 3 times that of 0.150 at 0.450 molar. For our next lesson, we're going to begin talking about what makes an acid different than a base, but for the time being, this concludes our review of how to work with solutions in chemistry.